Hello everyone and welcome to another video. So today I'd like to talk about similarity transformations. So within the context of linear algebra, we're going to see that similarity transformations involve two matrices which are related to one another. They're somewhat close and they share some properties, and therefore, as the name suggests, they're similar to one another. So what I'd like to do today is let's just go over the definition of what is a similarity transformation and then go over some of these properties that these matrices share. We're going to see later that one of the most useful applications of similarity transformations is to perform what's known as diagonalization, and we'll talk about that. Before going into some examples, we'll do two examples, one using what's known as a non-defective matrix and the other using a defective matrix, just so we can see the difference. And again, this will make sense what these two mean when we get there. So if that sounds like fun, why don't we just go ahead and jump right into it. So what's the definition of a similarity transformation? It's actually really simple. So the definition is that if you have two square matrices, square meaning they're of dimension n by n, let's call these matrices A and A tilde, okay? These two matrices A and A tilde, they're called similar if there exists an invertible square n by n matrix. Let's call this matrix T for like a transformation or a similarity transformation matrix, such that you can basically take A, left multiplied by T inverse, right multiplies by T, and you get A. So in other words, A tilde is equal to T inverse AT. So if this is the true, if you're able to find this matrix T, you basically have these matrices A and A tilde which are similar to one another. We're going to see what that means. It means that A and A tilde share some properties. In fact, why don't we start talking about that right now? Let's go through. We're going to see there, in this discussion, I'd like to talk about 5 different properties of the matrices A and A tilde, and we'll see how they relate to one another. Okay, so the first property that I'd like to investigate is the determinant of A and the determinant of A tilde. And we're going to see that actually both of them have the exact same determinant, okay? So to do that, let's go ahead and make use of a couple of matrix properties. And again, in this video, I like to focus just on the similarity transformation, not some of these individual matrix properties. So for example, I'm just going to pull this out of thin air. You feel free to verify this if you'd like, but if you recall, right, the determinant of a matrix, if it's a product, let's say A times B, right? This is the same thing as the determinant of A times the determinant of B. Okay, so we're going to make use of this. And in fact, in order to avoid writing det all the time, I'm just going to refer to this as A times B determinant, right, is equal to determinant of A times, whoops, oh, sorry, I did it. Right here, I'm trying to avoid writing det all over the place. So I'm going to use this bar notation to represent a determinant, okay? So let's recall this. This is one property of determinants that we're going to use. The other one that I'd like to everyone to remember is if you have the determinant of a matrix inverse, this is actually the same thing as the determinant of the matrix to the -1, or 1 over the determinant of the matrix, okay? So these are properties P1 and P2 maybe. Again, these are just properties of determinants. They have nothing to do with similarity transformations. This is just how determinants of matrices work. Again, feel free to verify this on your own, but now let's apply these two to our definition of our similarity transformation and see what pops out. So let's go ahead and investigate what is the determinant of A tilde, right? Well, the determinant of A tilde, well, we said A tilde is just T inverse, T inverse AT, right? Okay, now let's go ahead and use P1. This is a product of 3 matrices, so I can break them up into individual determinants. In other words, I can write this as T inverse determinant times the determinant of A times the determinant of T, okay? Great, and now let's go ahead and use this P2 property, right, where we can see that this is the inverse of T, so that's just 1 over the determinant of T. So in other words, this first term can be rewritten as 1 over the determinant of T, right, times determinant of A times the determinant of T, right? And we remember that the determinant, it's just a scalar value, right? It's just a number. So this determinant in the numerator is going to cancel this determinant in the denominator. So we end up with the determinant of A tilde B is actually equal to the determinant of A. So this is fascinating that basically under a similarity transformation, the determinant remains unchanged, right? So even if you provide you perform this similarity transformation, as long as T is invertible, you can use absolutely any T and it's not going to change the determinant. A tilde will still have the exact same determinant as A, basically the same determinant that you started with, okay? So that's the first property. Let's go ahead and look at another property. Okay, so the second property that I'd like to investigate, and we're actually going to see that the characteristic equations of both A and A tilde, right, the matrix characteristic equations, we're going to see they're the same. And therefore, if you remember, you solve the characteristic equation of a matrix in order to find its eigenvalues. So if the characteristic equations are the same, the eigenvalues are going to be the same, right? So let's go ahead and prove that right now. So if you recall the definition of an eigenvalue slash eigenvector, right? Do you remember this? For matrices, this is very common. It basically says, let's start with the matrix A, right? So AV is equal to lambda V, right? So if this is true, then lambda is an eigenvalue of the matrix A, and V is the associated eigenvector of that matrix A, right? So let's go ahead and rewrite this. So I can rewrite this as basically A minus lambda times the identity matrix times V is equal to 0, right? That's the exact same thing. Basically move it off to the other side, factor out the V. This is the same thing, right? And we see that basically the only way that this is true for a non-trivial V is that this determinant has to be equal to 0. So in other words, we see that basically this implies the determinant of A minus lambda I has got to equal 0, right? And this was basically your matrix characteristic. Whoops, sorry, I totally spelled that wrong. Characteristic equation, right? That's your matrix characteristic equation. Is you basically solve this thing for lambda, all right? Okay, so now let's go ahead and rewrite this using the fact that A is related to A tilde. So again, maybe it might help us if we come over here. Since T is invertible, right? I could just go ahead and left multiply by T inverse and, left multiply by T, right multiply by T inverse. In other words, I can rewrite this thing as what? It's T A tilde T inverse is equal to A. That's the exact same thing, all right? Okay, so now substitute this in for A, right? Okay, so we have, what do we have here? This is T A tilde T inverse minus lambda identity matrix. All right, the determinant of that whole thing has got to equal 0, right? Okay, let's go ahead and write this again. So I got T A tilde T inverse minus lambda. So the identity matrix, I can write this thing as T times T inverse if I want, right? That's the same thing as identity matrix is equal to 0, okay? So that's going to allow me to left factor out a T and right factor out a T inverse. So we end up with basically T times the quantity A tilde minus lambda identity matrix and then T inverse, right? The determinant of that whole thing has got to equal to 0, right? Now, this looks a whole lot like what we did in property 1. This is a product of 3 matrices, right? You've got T here. Whoops, that pen is totally dying. That's one matrix, here's the second matrix, here's the third matrix. Wow, that pen's also dying. Okay, so let's go ahead and use our property of, this is the determinant of the product of 3 matrices. Let's break this up into 3 individual determinants. So I have determinant of T, that's matrix 1, times determinant of A tilde minus lambda I, times the determinant of T inverse. Right, that's got to equal 0. Okay, now we do the exact same thing we did last time, right? This, well, let's not skip any steps, right? Times A tilde minus lambda I times, right? This is now the same thing as determinant of T to the -1, right? So again, this is a scalar number which cancels with that scalar number, right? So we end up with basically the same equation, right? We have determinant of a tilde minus lambda I is equal to 0, right? So this is the characteristic equation, right, for a tilde, right? This one up here is a characteristic equation for A, right? And it's basically the same thing. We basically see that this characteristic equation for A is the same thing as the characteristic equation for A tilde, right? So that shows this first part that we have the same characteristic equation, and basically since we're solving this characteristic equation to get eigenvalues, basically those together, right, basically just imply that both A and A tilde have the same eigenvalues. Right? So the eigenvalues remain unchanged underneath any similarity transformation. So as long as t is invertible again, you are not going to change the eigenvalues of A. A will have the same eigenvalues as A tilde even after you do this similarity transformation, right? So that's pretty interesting, okay? So I guess naturally your next question, since we're talking about eigenvalues, is what about the eigenvectors? All right, so we just showed that the eigenvalues of A tilde are actually the same as the eigenvalues of A. And actually, I should probably mention before we move on to the third property is this is true even with multiplicity. Let me write that down. Even with multiplicity. Meaning, even if there are repeated eigenvalues in A or A tilde, it doesn't matter. This is still going to hold true. Under the similarity transformation, you'll still have those same repeated eigenvalues showing up in A tilde, okay? So that's the discussion on the eigenvalues. So property number 3 looks at eigenvectors. And actually, this is where it's not the same, but they're similar. So we're gonna take a look at that right now. So to do that, maybe what we should do is let's go ahead and consider just a single pair. Consider a single eigenvalue slash vector pair. And I'm going to denote this as how about lambda I and vi, right? So this is basically an eigenvalue eigenvector pair of A. How about, let's call this of the original matrix A, okay? So vi, again, we saw lambdas don't matter, right? The lambdas for A are the same thing as the lambdas for A tilde, okay? But V, I want to make the distinction here that I'm going to use the notation vi to denote this is an eigenvector associated with eigenvalue lambda I of the original matrix A, okay? So that's, we've got that on the board. So now let's go ahead and take a look at, well, how does this relate to eigenvectors of how about A tilde, okay? So let's just look at A tilde, okay? Okay, and what I want to do now is let's just multiply this by some arbitrary vector. How about ui? Okay. Now again, A tilde, we said A tilde was, well, I guess we had it right here, right? A tilde is T inverse AT. So again, since I multiplied on the right by this arbitrary vector, I better do it over here as well. Okay. All right. So again, this UI is just some arbitrary vector. Okay. Now, since it's kind of arbitrary, why don't we go ahead and make it equal to, let's just use, how about the eigenvector of A multiplied by T inverse, right? Let's just pick this, okay? So this is going to be my u that I want to multiply it by, okay? Great, so let's go ahead and substitute that in over here. So what do we end up with? We end up with T inverse A T times T inverse VI, right? Okay, so these here, basically this is lucky, this becomes basically the identity matrix, right? That helps us. So we end up with T inverse AVI, okay? Now, you remember, what's the whole deal? What is AVI? Remember, the idea with an eigenvalue eigenvector, right, is the definition of an eigenvector is this, right? because V is this magical eigenvector, if I multiply A by itself, I basically get the same eigenvector just scaled by the eigenvalue, right? So this is, again, this is the definition of the eigenvector lambda I and its associated eigenvector Vi for the matrix A, okay? So great. This here, I can now just plug in, this AVI is the same thing as lambda IVI. So let's substitute this in for that, okay? So we end up with what? The T inverse is still hanging around, and we now end up with lambda I VI. All right, and again, now the nice thing about, since lambda I is just a scalar number, right? It's not a vector, it's not a matrix, it's a scalar, so I can just move this to the front with no hassle. So this is the same thing as lambda I T inverse VI. Right? Okay. And now, I'll tell you what, let's come over here on the left side. What was the left-hand side? The left-hand side is just, I haven't manipulated this at all. So this is still A tilde UI. All right? Okay, now look at this UI here. Remember, what was UI? UI was this up here, right? This was UI, right? It's T inverse VI. Okay, so let's go ahead and plug that in for UI. So maybe what I'll do is I'll just make a little note so we can recall what we're doing. So we're going to say, recall that UI, right? This arbitrary vector that we're using, it's T inverse eigenvector VI, right? So I'm going to plug that in over here. So we end up with A tilde, okay, A tilde, sorry, where? Yes, okay, T inverse VI is equal to lambda I T inverse VI, right? Oh, no, yeah, you know what I actually wanted to do? I actually wanted to, I wanted to make it the other, sorry, let's do this the other way around. This is the other way around. I wanted to keep the U here. So I wanted to make this a substitution. This thing right here, this is UI. Right? Yeah, that'll do better, right? Okay, so this thing right here, that's UI, right? So we basically have A tilde UI is equal to lambda I UI, right? Perfect. And this is perfect because if you stare at this thing long enough, right? This is, again, this is basically the definition of an eigenvalue eigenvector pair for the matrix A tilde here, right? Because this is basically saying matrix times some vector is equal to the same vector just scaled by this value, this scalar lambda I, right? So again, this is the definition of an eigenvalue lambda I and eigenvector UI, right, for A tilde, for that matrix, right? So what we can deduce from this is the only U, this has to be an eigenvector, right? So we basically see that UI, right, is an eigenvector associated with lambda I for the matrix A tilde, right? And again, what is UI? So we see here that this is how the eigenvectors, right? So we see this U is actually an eigenvector of A tilde, and it's related to the eigenvectors of A through this T inverse matrix, right? So at the end of the day, what we end up with is, shoot, I ran out of room. I guess I can write it over here. So the end of property number 3 is basically, it's the eigenvectors of A tilde are basically, they're the eigenvectors of A, but then you have to pre-multiply by T inverse, right? So this is the takeaway for property number 3, is that the eigenvectors of A tilde are related or similar to the eigenvectors of A, but they're not exactly the same. You need this T inverse. And again, this maybe highlights the fact of why we needed T to be invertible, right? So again, as long as T is invertible, this is true, and again, should hold true even if you have multiplicity of eigenvalues, right? So this is always is how you can find the eigenvectors of A tilde if you know the eigenvectors of A, right? So great, that's interesting for this property. All right, give me a second to erase the board and let's move on. All right, so property number 4 of similar matrices is actually they have the exact same trace. Now remember, the idea with the trace, the definition of the trace of a matrix A, remember again, we're talking about square matrices, it's just the sum of all of the diagonal elements, right? So you just basically take the 1, 1 element, add to the 2, 2, add to the 3, 3, add to the 4, 4, blah, 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 add to the n, n element, basically just sum up all the entries along the diagonal. That's the definition of trace. And again, we are going to use some properties of the trace. I'm not interested in deriving those or proving those here. We're just going to use them, but we will apply them to our similarity transformation. So again, the property I want to use for trace here is that, again, if A is the product of two matrices B and C, and actually these two don't even have to have the same dimensions. They have to have compatible dimensions, but they don't have to be the same. So for example, B could be of n rows by m columns, and C, I guess in order, this better be m by n, right? So at the end of the day, we have an n by n matrix A. Okay, so if we're looking at the trace of B times C, right, that's actually the same thing as a trace of C times B. Obviously, again, this times is matrix multiplication, right, as you can kind of clearly see here. Okay, so that's the property I want to use. Let's go ahead and apply that to our similarity transformation and see what we end up with, right? So let's go ahead and compute the trace of A tilde. Right? So again, A tilde, right, we said was just T inverse AT, right? So let's break this up into two steps, right? So let's go ahead and make a substitution. Let's go ahead and just say, I'm going to call this matrix B as just T inverse, and let's call the matrix C as sort of the this matrix AT, right? So this bit right here, let's just call this matrix B, and let's call this matrix C. Right? So then, using our trace property where I can basically just flip the order of these matrices, right, we end up with, this is the same thing as trace of AT times T inverse, right? And then this is super easy because now this becomes an identity matrix and we basically end up with just trace A, right? So we see that trace of A tilde is the same thing as trace of A. So again, pretty interesting. We see that the trace of the matrix, again, is not changed under a similarity transformation. All right, so with property number 5 concerns the matrix rank, right? And we're actually going to see that again, A and A tilde have the same matrix rank. So again, just to refresh your memory, the idea with the rank of a matrix, right, is it's basically the dimension of the space spanned by the columns of this matrix A, right? And again, the other way to think about that, it's the number of the maximum number of linearly independent columns of the matrix A, right? So if we take that perspective of what the rank of the matrix is, you can see that basically if you have a matrix A, right, and you operate or transform on this by some invertible T, right, you're basically not changing the number of linearly independent columns of that matrix, right, because T is invertible, right? So basically you can see that the rank of this thing is the same thing as the rank of A. Right? You haven't changed the rank of it by multiplying by an invertible T. And in fact, the invertible T can be on this side or it can be on the other side, right? It doesn't really matter. In fact, here, I'll tell you what, let me do this. Let me write this, right? All of these are the same thing, right? For T invertible. Right? Because that's the whole idea with invertible, means that T is full rank, right? It doesn't, it's not singular, it's full rank, so it's not going to change the number of linearly independent columns of the matrix A by just multiplying, right? And in fact, you can think about this the same way of, you know, again, you have A, here's another invertible matrix. How about T inverse, right? Because T is invertible, T inverse is also invertible. So it's the same idea, right? I've got an A, I've got some full rank matrix that I'm multiplying it by. So again, I can multiply it by that on either side, right? And you still end up with rank of A, right? Again, for T invertible, right? So again, let's go ahead and we'll put these in the bank. Right? The other way that we could prove this, if you want to make sure that this is true, right, is again, we can use the property of matrix rank that says that the rank of A times any matrix T, right? Again, let's forget about T being invertible for now, but this is the product of any two matrices. If you take the rank of this rank has got to be less than or equal than the minimum of the rank of A and the rank of T. Right? So we can note now, if T is invertible, well, actually, maybe tell you what, let me take away the if, right? Let's just make the statement that, right, if you have T invertible, right, this basically only happens if and only if the rank of T, right, is equal to the full dimension of the space, right? So this only happens if rank T is equal to n for our square matrices, right? So therefore, I think if you look at this minimum, you know that the rank of T has got to be greater than or equal the rank of A. So we can basically write that if T is invertible, we have rank of the product AT. It's got to be less than or equal to the rank of A. Right? Let's tell you what, let's I don't want to box this, but maybe we should star this or number this. In my notes, I've got this as equation 6b. Let's just use my same numbering so we don't get mixed up. And I could basically, you know, we could do a very similar thing. Let's just actually use 6b again, but let's go ahead and change the matrix. So I'm going to look at the rank of a product of two matrices. Let's just, instead of A, let's turn this into the product AT. And instead of T, let's turn this thing into T inverse. Okay? So what I mean by that is now we have the rank of the matrix, this thing, AT, right? That's that one, times T inverse, right? This thing has got to be less than or equal than the min of the rank of AT, right, and the rank of T inverse, right? Okay, so again, this, we can write the left-hand side, this is basically going to be rank of A, right? And again, we see that this here is full rank, right? So rank of T inverse, because T is invertible, T inverse has to be invertible, so the rank of T inverse, this has got to be n. So this has got to be bigger than this. So we basically have, this has got to be less than or equal to the rank of AT, right? Okay, so let's call this equation, how about 6c, right? If you look at equation 6b and equation 6c, you see the only way these two are satisfied simultaneously, right, is if the rank of A is equal to the rank of AT, right, because it's on the opposite side of the less than or equal sign on both sides. So basically combine 6b and 6c and we end up with basically the rank of AT has got to equal the rank of A. Right? And again, this is exactly what we did up here. And again, you could do the exact same thing for TA, which is this part of it. And again, you can do the same thing with T inverse. So again, this discussion here, if you glossed over that, is basically just to get us and convince ourselves in the head that these two things are true. And I know I said we wouldn't try to prove too much of this, but I think this is maybe somewhat useful here because now it kind of gets us in the mood for applying this result up here to our similarity transformation. So yikes, I'm kind of running out of space. Let's come over here. How about? Okay, so let's go ahead and look at now, how about what is the rank of A tilde? Right? So the rank of A tilde is basically, well, again, what is A tilde? A tilde is just T inverse AT, right? Okay, so tell you what, let's again break this up into the product of two matrices. How about the rank of, let's group let's do T inverse A as one matrix and then times T, right? Now, pursuant to this set of equations, right, where we basically see that, again, this is the product of two matrices, and this is something here times T, which I know is full rank, right? So this is basically, I'm going to use this portion, maybe, so let me circle this in green, right? Where the rank of some matrix times an invertible full rank T is basically the rank of that original matrix, right? So this thing can be basically be written as rank of just T inverse A, right? It's just the matrix thing in parentheses, right? And now this is the exact same thing. You look at this and we say, okay, this is a product of two matrices. It's an invertible matrix times A. So again, you can kind of come over here and we could say this part, sorry, I should have put, right? This T inverse A is basically the same thing as rank A. So this is basically just rank A. So here you go. We end up with rank of A tilde is equal to the rank of A. So we see, again, the rank of the matrix is unchanged underneath a similarity transformation. All right, so that was great. We saw that similarity transformation preserves a lot of properties between the matrix A and the transformed or similar matrix A tilde, with the exception of the eigenvectors, which we saw were somewhat similar and related. Now, remember, those properties that we just talked about are basically true for any similarity transformation as long as T is invertible, right? Now, what I want to talk about now is one of the most useful types of similarity transformation. So I would like to look at a particular T that is going to diagonalize your matrix. So what we're going to see is the matrix A tilde that you end up with is going to hopefully be diagonal. It's going to have only values along the diagonals and zeros everywhere else. And again, this process is known as diagonalization because we're going to take a matrix A, which is, might have entries all over the place, and then through a similarity transformation with a very specific T, we are going to be able to turn that A tilde matrix completely diagonal. So to go about that, we're going to see this has something to do with the eigenvalues and eigenvectors of a matrix. So again, remember that for your matrix A, right, the idea with the eigenvector, let's call it VI, is that if you multiply it with A, you basically get that same vector but scaled by the eigenvalue, right? So again, this is for n equals 1, 2, all the way up to, or sorry, for I equals 1, 2, all the way up to n, right? So tell you what, let's write this out as, n separate equations, right? So you could write this as basically, AV1 equals lambda 1 V1, right? AV2 is equal to lambda 2 V2, etc., all the way down to AVN is equal to lambda n Vn, right? So these are basically n equations, right? Individually, one of them at a time, okay? So what I would like to now do is, how about let's stack all of these up together. So what I mean by that is I would like to take this first, let's look at this one equation, right? Again, maybe we should be a little more specific. This is n equations, and it's an n sort of vector equations, right? Because this first equation right here, it basically says this is a vector is equal to another vector, right? And it's an n element long vector. So you can think about the left-hand side, this AV1, right? It's an n by 1 element vector. So you know what? Let's stack this. Let's start making a matrix where this first column is going to be this thing here, right? So this is going to be AV1, right? So I'm going to basically just take this first part here, put it over here in the first column of this matrix that we're going to build up, okay? And again, let's leave the entries over there as something else, and I guess we're going to take a look at that in a second. This is equal to, you could write this as, and again, let's write it again as another vector over here. The right-hand side of this is lambda 1 V1. Would everyone agree? That's the same thing. So I'm basically just taking this part and jamming it in over here. So these, again, you can think about these as vectors if that's helpful, right? So I haven't rewritten anything. I've just stacked it up. So this first equation is basically the first column of this matrix, right? Let's do the same thing for this second column of this matrix. Is going to be the second entry. So this is going to be AV2, right? That's this column is equal to lambda 2 V2, right? Right, etc., etc., as you can see, and we're going to go all the way down to AVN is equal to lambda n Vn, right? Right? Okay. Okay, so this is basically, again, think about the dimensionality. This entire matrix here is a n by n square matrix, right? Because this vector right here, this is an n by 1, this is an n by 1, and all the way down to an n by 1. So you basically stack up all of these together, and you have this n element vector, n element vector, n element vector. You stack up n of them, you end up with an n by n matrix, right? And same thing over here, right? This thing is an n by 1, this is an n by 1, all the way up to an n by 1. So you stack them all together, so this whole thing is an n by n. So you basically, again, we now are basically taking all of your eigenvalues, eigenvector pairs, and we're just writing them as basically a matrix equation, right? So now, you know what we can do? Tell you what, let's move everything over to one side, okay? So what I mean by that is I'm going to drop that this sort of vertical vector notation, because I think we all understand that AV1, if this is a vector, AV2, this is a vector, all the way up to AVN. This is a vector, right? And I want to move this to the other side. So I have to basically say minus, right? Lambda 1 V1, lambda 2 V2, all the way up to lambda n Vn, right? This has got to equal, it's a bunch of zeros, right? Because I moved it over to the other side. So this is basically a n by n matrix of 0. So you can think about this as like, again, a 0 vector here, all the way up to another 0 vector, right? And again, each one of these is an n by 1, all the way up to n by 1. So you end up with an n by n. So again, same thing. Well, I'm doing nothing more than just rewriting these n vector equations in matrix form, right? Okay, so now what's great about this is let's examine this first term here. You notice A is pre-multiplied everywhere, so let's pull it out on the left. So this can be rewritten as A times V1, V2, all the way out to Vn, right? Okay, minus, let's look at this thing, okay? This thing, lambdas, right? Remember all these eigenvalues, they're just scalar numbers, right? So if you stare at this n by n matrix long enough, you'll basically see that you could write this whole thing as V1, V2, all the way up to Vn, times a diagonal matrix, which is lambda 1, 0, 0, basically it's lambda 1, lambda 2, all the way down to lambda n on the diagonals, and zeros elsewhere. So you can write it as a diagonal matrix. So again, take a little while to convince yourself of this, that this matrix, which again is an n by n, right? This whole thing is an n by n, and so is this thing. This is an n by n matrix, right? The product of these two is this term up here, right? Okay, so again, this is equal to, again, this big giant 0 matrix on the other side, right? Okay, great. So now, actually, sorry for moving things back and forth, but again, let's go ahead, move this to the other side, right? So let's take all this thing, move it to the other side. So we basically end up with this thing where it's A times this V1, V2, Vn matrix is equal to this V1, V2, Vn matrix times this diagonal matrix of lambda 1, lambda 2, all the way down to lambda n, and zeros elsewhere, right? Now, this is fascinating because if you stare at this, why don't I call this matrix here T? This is my similarity transformation matrix, right? Because it shows up on both sides, okay? And let's call this thing here, let's call it A tilde, right? So if you look at this, if we go ahead, we can write this now as A T is equal to T A tilde, right? Okay, and now here's the rub. This is fine. This is true so far. So if you look at what we did here is we chose our transformation matrix T to basically be this V1, V2, all the way up to Vn. So what this transformation matrix is, this is a matrix of the eigenvectors, right? Stacked up in column format. And again, I'm going to call that out in column format because depending on what software packages you're using, for example, Mathematica gives you eigenvectors of a matrix in row format. That's not what we're doing here, right? This matrix T is the first eigenvector as a column, the second eigenvector as the next column, etc., all the way up to the nth eigenvector as a column here, right? But this is the very special transformation matrix, okay? And this is true no matter what, okay? So we actually haven't done a full similarity transformation matrix, a similarity transformation yet because I haven't isolated A tilde, right? Now, here's where we got to pay a little attention, right? Now, if T is invertible, right? If T is invertible, that's great because if that's the case, what can I do? I can basically isolate A tilde and we end up with our usual A tilde is going to be T inverse A T, right? Okay? And what's special about that is look at the form that the A tilde took, right? So again, A could have been anything, right? But if we use a similarity transformation of the eigenvectors as our similarity transformation matrix, we end up with this A tilde format where you have the eigenvalues falling along the diagonals and there's zero elsewhere. So this A tilde is a purely diagonal matrix, right? Which is very, very, very nice for a lot of different reasons, right? And again, the thing that we have to, I want to really hammer home is that this is true if it's invertible, right? If it's invertible, we can diagonalize a matrix, right? If it's not invertible, this is still true, right? A times the eigenvectors, it should be equal to the eigenvectors times your eigenvalue diagonal matrix here, right? That should still be true. But you're not going to be able to get all the way down to this relationship if T is not invertible. So again, I think I'm hammering this home, and maybe I'm talking about this too much. But again, I want to stress the fact that this is very, very useful. We're going to see this show up over and over and over, and especially in control systems and linear system theory. This is sometimes referred to as a modal form, and sometimes this T is sometimes referred to, maybe let's just write that down. T is sometimes known as the modal matrix, modal, M-O-D-A-L, modal matrix of A. Okay, and again, T is just the eigenvectors of A stacked up in column form, okay? And again, I think it's beyond the scope of the lecture today to talk about what does it mean for, what does the word modal mean? We will talk about that in other discussions when we look at linear system theory and dynamic systems. I think it'll be much more clear why this is called a modal matrix, but for now, we can see that the power of this is that it allows us to diagonalize a matrix, and we see there are some caveats, right? We have to ensure that the eigenvectors basically span the space, right? If all the eigenvectors stacked up column-wise are full rank, right? That means this T. Hold on, let me get that straight. If the eigenvectors are all linearly independent, right? Meaning the eigenvectors span the space, then T will be invertible, and you can diagonalize a matrix, right? So again, this is a little bit. It might help us understand. For example, if you look at the Wikipedia page on diagonalization, in fact, here I'll flash up a screenshot of the text there, right? And it says basically, right, you have a square matrix which is diagonalizable if and only if, right, the sum of the dimensions of its eigenspaces is equal to n, right? The full space. So basically, that's exactly what we're talking about, right? If the eigenvectors span the space, then the matrix is diagonalizable, all right? You can perform this diagonalization procedure, okay? Now, if it's, and in that case, A is sometimes referred to as a non-defective matrix because it can be diagonalized, right? If it cannot be diagonalized, it's sometimes referred to as a defective matrix. And in fact, that's what I want to look at right now. Why don't we take a look at an example of all of these with those two situations, a non-defective matrix and a defective matrix. So we'll run through all the properties we talked about. We'll show those properties are true regardless if the matrix is defective or not. But we'll see that this diagonalization is only possible for a non-defective matrix. All right, so here are the two example matrices that I'd like to look at. So the first one is a non-defective matrix. So we'll see that this one has eigenvectors which span the space. And again, that only matters for our discussion on diagonalization. We can show that this matrix, when we go ahead and use a similarity transformation, namely I'm going to use this similarity transformation of T here to basically compute our similar matrix, we're going to see all those properties hold, properties 1 through 5, regardless if it's defective or not. And we'll see that since this matrix is non-defective, we'll then be able to use another transformation matrix, which I think we're going to call it M instead of T. We'll use M to denote the modal transformation, which is just the eigenvectors. And we'll go ahead and look at diagonalizing that matrix A, okay? And then the second example, I just like to look at a slightly different matrix. It's the same as the first matrix. The only entry that's different is this red one in the 1, 1 position. So instead of a 3, let's make it a 5. This matrix is actually defective, so its eigenvectors do not span R4 in this case. But again, we will go ahead and use the exact same transformation matrix here to perform our similarity transformation, and we'll see that still, even though this matrix is defective, properties 1 through 5 still hold. It's just going to be an issue. We're not going to be able to diagonalize this matrix using the modal transformation of its eigenvectors. So why don't we jump over to MATLAB and actually do this, because it'll be a lot quicker and easier just to have MATLAB do a lot of these operations. All right, so here we are. I've just written a little bit of code ahead of time to save ourselves some headache. And as you can see, I'm just going to go ahead and get the non-defective matrix to start with. So let's go ahead and run this. And okay, here is our transformation matrix, our similarity transformation matrix that we talked about up on the board. So again, let's just go ahead and run to the next breakpoint to get T into the system. Now, let's again make sure that T is invertible. So let's compute its determinant, and we see, yep, that does not look anything near 0, so I think we are good to go. T is definitely invertible. So we should be able to perform our similarity transformation matrix here using just T inverse AT. So let's go ahead and do that, and as you can see, we get something totally different than what we started with, right? So here was A, and now here's A tilde. It looks completely different, but as we discussed on the board, a lot of these things are the same. 4 properties should be the same, and the 5th one, right, the eigenvector should be very similar. So in fact, let's just go ahead and take a look at this. So property 1, the determinant, right? Both determinant of A and A tilde, those should be the same. So let me just execute that, and we see, yes, the determinant for both matrices is 20 in this case. How about the eigenvalues? So MATLAB, remember, has a function called EIG, which is going to give you the eigenvalues in a diagonal matrix D and the eigenvectors in column format as a matrix V. So that's what I'm doing right here. I'm going to look at the eigenvectors of A and the eigenvalues of A, and then we'll look at the eigenvectors of A tilde and the eigenvalues of A tilde here. Again, maybe let me put a breakpoint right here, and I'll run just to this point, and we can look at, in this case for property 2, I only care about eigenvalues, so let's look at D, right? And as you can see, D is basically a diagonal matrix. I guess if we look at this, let me open up. You can see it's a diagonal matrix. These are all zeros. If you look at 0 plus 0i, that's what all these other entries are. So there's only entries along the diagonals, and the diagonal entries are the eigenvalues. So that's what the eigen function is giving us. So it looks like for this matrix A, there's an eigenvalue at 3 plus 1i, 3 minus 1i, 1 and 2, right? That's the eigenvalues. So I'm actually going to rip them off using the diag function to just extract the diagonal entry. So again, if I F10 this and run that line, you'll see that lambda here, this is a list of all the eigenvalues of the matrix A. So again, it's like we said, it's 3 plus 1i, 3 minus 1i, 1 and 2, right? Let's do the same thing for A tilde. And here you see that it's the same, but a little bit different in the sense that the ordering is different. So look, the first two eigenvalues have the exact same value and order, but then you see that for whatever reason, MATLAB's eigen function decided to return us the eigenvalues in a different order. But regardless of that, the eigenvalues are actually the same. We just need to be a little bit careful that for whatever reason, MATLAB decided to give us the eigenvalues in different orders. Therefore, this matrix of eigenvectors are also, we got to be a little careful how we're going to play with them. Right? But again, this is enough to prove property 2 that basically, well, not basically, they are the same, right? The eigenvalues of both A and A tilde are the exact same. Now, let's look at the eigenvectors, right? We discussed on the board that the eigenvectors of A tilde should basically be the eigenvectors of A, but then we have to multiply by inverse T, right? So that's what I'm going to do right here. I'm going to compute what are the eigenvectors of A tilde. What should they be using our relationship we derived on the board of T inverse times the eigenvectors of A, right? Now, what I'm going to do here is I wrote myself a small little function called R matrices same. So don't try to search for this function on the MATLAB help. It's my own custom function, but I'm just checking to see if two matrices are the same within some tolerance. In this case, it's 10e to the minus 10, so it's some very small value. So as you can see, what I'm doing right here is I'm checking that this quantity A times the eigenvector 1, right, or what I think the eigenvector should be using this equation, should be equal to the eigenvalue of A tilde, which is the exact same thing we just showed as the eigenvalue of A and A tilde, the exact same thing, right? But multiplied by this eigenvector of A tilde, right? So what I'm doing here is I'm checking to make sure that this thing, what I'm calling eigenvector tilde, is actually the eigenvectors of A tilde, right? So all of these should come back and say true, true, true. So let me just step through this, step. So yep, the first one matches, right? So this first eigenvector is correct. The second eigenvector matches, the third one matches, and the fourth one matches. So I know that this thing right here, this eigenvec tilde, this is in fact the four eigenvectors of A tilde, right? That's what we just proved. So that's great because you saw we actually, I did not use this at all, right? I did not use the eigenvectors that the MATLAB function I computed for me. I used the eigenvectors of the original A matrix and then used our similarity transformation to get those eigenvectors, right? So this is great. It shows property 3 it works for this case where the eigenvectors are similar. They're related to the original A matrix eigenvectors through this transformation. And the last two properties are almost trivial, right? So again, I'm just going to look at the trace. Let's take a look at both those. And we see, yeah, in both cases, A and A tilde both have a trace of 9, and they should both have the same rank. So both of them have a rank of 4. Now, let's talk about diagonalization. So again, we just saw that those 5 properties were fine regardless of the similarity transformation. Now let's switch gears and talk about diagonalization. So in this case, I do want to use a transformation matrix. I'm going to call this the modal transformation matrix M, and I want that to be the eigenvectors of the original A matrix. So again, make sure we're very clear on this, right? This matrix V, this is the eigenvectors of A, not A tilde. So if I use the eigenvectors of A, I can go ahead and perform my similarity transformation here using the modal transformation matrix, and I should end up with a purely diagonal matrix with the eigenvalues along the diagonal. So again, let me just step, 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 and look at this. Diagonal, this totally worked, right? If you remember, what do we call this thing? I think I made a variable lambda, right? This was the eigenvalues. It was 3 plus or minus 1 and 1 and 2. And look at this. Here's 3 plus 1. Here's 3 minus 1. Here's 1. And then here's 2. All along the diagonal. So indeed, this similarity transformation, or this modal similarity transformation, has gone ahead and diagonalized my A matrix. So this A tilde, which I call the diagonal, is indeed diagonal. So in this case, it totally worked. And when I say it totally worked, I mean the diagonalization process worked for this non-defective matrix, okay? Now, let's go ahead and change this. Instead of using a non-defective matrix, let's use the defective matrix and go through this exact same exercise. So again, let's go ahead and I guess I can take all these breakpoints off because none of this is going to change. Yeah, this transformation matrix is still going to be invertible. I can still go ahead and compute A tilde, which again here, looks a little bit different, all right? But again, we should be able to see that all these properties are the same. So again, let's check the determinants. Yep, in both cases, the determinants are now 32. I think it was 20 earlier, but again, it doesn't matter that because they're both the same. We can also see that the eigenvalues are also the same. So now in this case, now look at this. We've got multiplicity of the eigenvalues here. We've got a 4 and a 4, okay? Which is going to potentially cause us problems when we start looking at the eigenvectors. But again, what's important to note here is that both A and A tilde have the same eigenvalues, namely 4, 4, 1, 2. And again, look at this. For whatever reason, the ordering is different, but still, it's 4, 4, 1, 2, right? Same eigenvalues. And again, we can do the eigenvectors. Let's go ahead and compute the eigenvectors. So again, I'll just hit F5, run through all these, and we see that, yep, checks out 1, 2, 3, 4. So all 4 of these eigenvectors, they are eigenvectors of the A tilde matrix. Now, what's interesting is maybe we should interject here is if we look at this eigenvector matrix, if we look at the rank of this thing, look at that. The rank is only 3. So in this case, the eigenvectors of A tilde do not span the space. And in fact, the same is true of the rank of the eigenvectors of A. And in fact, that's probably what we wanted to look at in the first place, because this is what we're going to use down the road when we start talking about diagonalization. And again, look at this. It's also rank 3. Okay, well, keep that in the back of our head. We'll revisit this in about 60 seconds, but in the meantime, let's go ahead and convince ourselves that even with this defective A matrix, doesn't matter, the traces are the same, right? In this case, they're both 11, and now the rank of A and A tilde are the same, and again, they're still full rank, right? There were no 0 eigenvalues, but the eigenvectors, now this is where we come to it when we start trying to do diagonalization. So if I tried to use a transformation matrix M, which is now the eigenvectors of A, the problem with this, as we saw earlier, is the rank of this thing is only 3. So I can't actually do this. You cannot diagonalize any longer. You can't go ahead and say inverse M, right? This is going to fail, right? Because this thing there, look at this. It is singular or badly scaled, so it's not going to work. And again, when I say it's not going to work, we mean that we can't diagonalize the A matrix in this case because it's a defective matrix and its eigenvectors do not span the entire space, okay? So now this could be ameliorated to some degree by investigating what's known as Jordan normal form, but again, I think that's outside the scope of this discussion. We'll try to have another discussion in another video later discussing Jordan form of matrices, but for now, I think this is a good discussion showing an example of all of these different properties under the similarity transformation. All right, so there you have it, a pretty mathematical, sort of sterile approach and discussion and investigation on similarity transformations. In our immediately following video, we'll take a look at trying to apply this to an engineering problem of basically changing the states in a linear system using a similarity transformation. We're going to see how this might be actually applied to some control or dynamic systems applications. So, with that being said, I think this is probably a great spot to leave it. I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel. If you scroll a little ways down and click on that subscribe button, it really does help me continue making these videos. The other way you can contribute and help the channel is via Patreon. I want to take a moment to thank some of our recent patrons. The nice thing about this method is that 100% of the proceeds that the channel receives via Patreon is going to be directed to K through 12 science, engineering, and adventures for kids and young adults. So, speaking of the new videos, also remember they should come out every single Monday, so I hope I'll be able to catch you at one of these future discussions and we can all learn something new together. So, until then, I think I'll sign off. Talk to you later. Bye.